Okay, welcome to 5.1, and today we're going to discuss growth and decay and integral exponents. The objective will be to define and apply integral exponents. So, let's start with a hamburger. All right, now the cost of hamburgers has been increasing by 9% per year. So if I go down to my local Egan's, every year that burger is getting more and more expensive. It is increasing by 9% every year. This implies each year the cost is blank times the cost of the previous year. Well, first, think about that 9% as a decimal. That would be 0.09. Okay, so that's the percent of increase right there. And to represent 100% of my hamburger, I'm going to put a 1 in front of that to get 1.09. So each year the cost is 1.09 times the cost of the previous year. This is called a growth factor right there. And every exponential function has a growth factor. If the cost this year is $4, what is the projected cost for 1, 2, 3, and t years down the road? Now, they're having you look at this so you can kind of develop how you can easily set up an exponential model. We're going to start with a little table right here. All right, so we're going to have our independent variable time and then our dependent variable cost. Cost depends on time. And we'll start today at 0 years. All right, and what is the cost of that burger today? It is $4. And then in 1 year, what would the cost be? Well, it would be last year's cost times the growth factor of 1.09. And then in 2 years, it would be the original cost, but then it'd be times the growth factor, but that's the growth factor for year 1 and then the growth factor for year 2, which means I'm going to go 4 times 1.09 squared. So you see what's happening right here? And look at your patterns. This is 4 times 1.09 to the 0 power. This is 4 times 1.09 to the first power. This is 4 times 1.09 to the second power. How about year 3? Do you think it might be 4 times 1.09 to the third power? Because every year the cost of that burger increases by 9%. And then finally, t, let's come up with our formula. How about 4 times 1.09 to the t power? Notice, this is why they call this exponential. Our independent variable is the exponent. So, cost in terms of time is 4, the initial cost, times a growth factor of 1.09 to the t power. And again, c of t is an exponential function. The independent variable is an exponent. All right, so if we have t greater than 0, that would give us future cost of our hamburger. If t is less than 0, that would give us past cost. So we can answer a lot of questions with this exponential function representing the cost of our burger in terms of time. So find the cost of a hamburger 5 years from now. Well, all that is we're going to take this 5 and make that exponent t of 5. So on my calculator, I'm not going to do this in my head. I'm just going to go 4 times 1.09 to the 5th power. So what's the cost of this burger in 5 years? Well, if I punch out carefully now, 4 times 1.09 to the 5th power, I'm going to get $6.15. How about the cost of a hamburger 5 years ago? So that means this t now past cost would be a negative 5. So if I do that, 4 times 1.09 to the negative 5 power, I get $2.60. Man, if burgers would be that cheap, I'd be gaining a lot of weight. Let's be careful. All right, so next, set up a function for the cost of a $70 calculator that goes down in price by 9% each year. See, that's the thing. Hamburgers go up in price, And technology, because it becomes cheaper and cheaper for companies to make these things like calculators, goes down. So set up a function for the cost of a $70 calculator that goes down in price by 9% each year. So here's what I'm thinking. I'm setting up my exponential model right here. And I hope you notice that what is my factor out here? It's always my initial cost, $70. And then in the parenthesis, I have my growth factor based upon my growth rate. Now, think about this one. The calculator is going down by 9%. So 1 plus my growth rate would actually be 1 plus negative 0.09, which is going to be 0.91. Does that make sense, you guys? So I'm decreasing, so I subtracted this growth rate from 1 to get 0.91. And there's my exponential model. Now, let's play with graphing these, because I want you to kind of know what exponential growth and exponential decay looks like. And we have just seen an example of each of these. So exponential growth, it was our burger. And that was C of t equals, how much did this burger cost initially? It was $4. And it was going up by 9% each year, so my growth factor was 1.09, and that is to the t power. Now, exponential decay, that's the calculator situation. And the calculator was C of t equals, the calculator initially cost $70, and it was decreasing by 9% each year, so my growth factor was 0.91. Note, an increase of 9%, 1.09, a decrease of 9%, 0.91, and then to the t power. Now, let's graph these. And I love graphing an exponential function because I can see the y-intercept immediately. Okay? The y-intercept of 4 times 1.09 to the t power, well, that's my initial value. That's 4. 1, 2, 3, and 4. There it is. Now, the y-intercept of 70 times 0.91 to the t, it's going to be 70, which means I better rescale. So what did I do here? I probably went by 20s. 20, 40, yep, 60, so 70 would be about right there. Again, so in an exponential function, I see my y-intercept immediately. Now, I'm going to break out my calculator, and I am going to do a table. So I'm going to make y sub 1, 4 times 1.09 to the t. I'm going to make y sub 2, 70 times 0.91 to the t. And then create a little table, and let's see. Let's go from negative 3 to 1, 2, 3 to 3 on my table. So there it is right here. My x's are negative 3, negative 2, negative 1, 0, 1, 2, and 3. And then my y sub 1s, here's my outputs for my exponential growth, and here are my outputs for my exponential decay. So let's plot some points. So let's start, well, let me see, where do I start here? How about I start this graph with that negative 1 that I can see, and my output is 3.6697. So I'm just going to approximate that. So what? That's going to be what? About right in there somewhere. Okay. And then at 0, I already have my y-intercept. At 1, I'm at 4.36. 4.36, about right there. Okay. And then at 2, I'm a 4.7524. 4.7524, that's going to be about right in there. Okay. And then at 3, I am at 5.1801. At 3, I'm up here at 5.1801. About right there. Okay, so now, we don't have a lot of points on the scatter plot, but I hope you notice that this is not linear. I'm showing slight exponential growth here. So this will show some concavity opening upwards right here. Now, if we kept going and going, it would get more extreme and then just take off vertically. Not quite, but almost vertically eventually. Now, over here, this is exponential decay. So let's start at the point when t equals -3. And that would be almost 93. Okay, so where am I at? That's 60, 80, 90, 93 would be just above that hash mark. So I'm going to have a point, I don't know, about right in there. Not perfect. Let's see. Oh, I came in a little lower. Let's double check that. 20, 40, 60, 80. Oh, there we go. This is 100. So 90 be right here. Yeah, there's my 93. Can you hear my dogs in the background? Yeah, somebody's coming by. They're about to go crazy. I'm sorry, you guys. Roxy? No. I'm recording right now. Yeah, I know you understand that, don't you? All right, so at -2, I'm at 84.531. -2, 20, 40, 60, 80, 90 would be right there. So 84 would be about, I don't know, right in there. There you go. That's better. At -1, I am at 76.923. 20, 40, 60, 80. So 76 is going to be about right in there. Yeah. And then let's go to 1 on this one. 63.7. So at 1, I'm at 20, 40, 60, 70, 63. It's going to be about right in there. All right. And now this one, not linear, but a slight exponential decay. I'm still concave up, and if I kept going and going and going, I just approached the t-axis, but I'd never quite reach it. Okay, so there's a great example of a graph, exponential growth. 4 times 1.09 to the t. Note, if my growth factor is greater than 1, I'm going to have exponential growth. And here, my growth factor is 0.91. So my growth factor is less than 1, so I have exponential decay. Exponential model is A of t equals. Okay, now here it is, and I hope you've noticed this. What did we always start with? Our y-intercept. This is our initial condition right here, and we call that a sub 0. And then in the growth factor, we always have a 1 plus our growth rate. And we call that our r to the t power. There's your exponential model right there. So, a little bit, and I just kind of mentioned this, but I talked about the entire growth factor instead of just the growth rate. If the growth rate is a number between -1 and 0, all right, then I'm going to have exponential decay. Okay? So, a $70 calculator that goes down in price by 9% each year. So that's going to be a growth rate of -0.09 right there. Okay? Okay, here's our first story problem here. Suppose radioactivity decreases by 15% per day. If 40 kilograms are present now, find the amount present A, 6 days from now, and B, 6 days ago. So what we're going to have to do is set up our exponential model. Okay, and again, A of t, the amount of radioactivity, will equal A sub 0, our initial amount, times the growth factor, 1 plus our growth rate to the t power. Keep it simple. So A sub 0 in this problem, what do we start with? 40 kilograms of radioactivity. And what is our growth rate? It is decreasing by 15%, so that'd be -0.15. Now, let's just plug those into our exponential model right here, and then use our calculator to answer these questions. So, A of, well, 6 days from now, so A of 6, I'll go 6 here, and 6 as my t in the model. And now, what's my growth rate going to be? 1 plus -0.15. That would be 0.85. Okay, then I just punched that out on a calculator carefully, and I got approximately 15.1 kilograms in 6 days. Okay, and that's just going to get closer and closer to 0, but it's never going to quite get there, so don't pollute, especially bad things like radioactivity, by the way. Now, B, 6 days ago. So now my input's negative 6. We'll put it here and as our t in our model. And we're still at 0.85 right there. And now you just carefully punch this out. 40 times 0.85 to the negative 6 power. And when you put this in your calculator, make sure you put that in parentheses so you get the power of negative 6. And that was 106.1 kilograms approximately. Now, laws of exponents. This is critical. Laws of exponents have to become totally automatic to you guys. All right, so you need to know how to rewrite b to the x times b to the y. And all that's going to be when you're multiplying expressions with common bases, all you need to do is add the exponents. So b to the x times b to the y becomes b to the x plus y power. Now when you're dividing terms with common bases, then note over here, when you multiplied, you added the exponents. So if I'm dividing, I'm going to subtract the exponents. So that's going to become b to the x minus y power. Now, number 3, if b does not equal 0, don't want a base of 0 because 0 times anything is 0, 1 or negative 1, then b to the x equals b to the y, if and only if. So b to the x equals b to the y if and only if. Well, I have the same basis here, so this could only be true if x were equal to y. There you go. Same exponents. Okay, a times b to the x. Well, you have two factors to the x power. That means you could rewrite this with each factor to the x power. So that's going to become a to the x times b to the x. Now here's same thing, but we're dividing. A over b to the x becomes a to the x divided by b to the x. And by the way, b cannot equal 0 because that would give me 0 in my divisor there. So if x does not equal 0, and a is greater than 0 and b is greater than 0, now same thing, then a to the x equals b to the x if and only if, remember this symbol, if and only if right there. Well, now I have common exponents. So the only way a to the x would be equal to b to the x would be if a is equal to b. And then your last rule right here, power of a power. B to the x to the y. Well, up here, b to the x times b to the y was b to the x plus y. If you have a power of a power, you just multiply those exponents together. So that becomes b to the x times y power. And those are your laws of exponents. These are critical and must be automatic for your pursuit of advanced mathematics. All right. Now, a couple more very cool rules. You guys should know this automatically. B to the 0 power. Well, anything to the 0 power, we saw that when we were graphing our exponential growth and exponential decay. Remember the $70 calculator when t equals 0 was $70? Okay, so, you know, here's what's going on here. That 0 right there made my that growth factor was what? 0.91 to the 0 becomes 1 and just left me the $70. So anything to the 0 power is 1. And now negative exponents. We can't have negative exponents in final answers, so we have to be able to rewrite this. Okay, so b to the negative x. Well, if I want to get rid of a negative exponent, I'm going to move up or down. This right now is a b to the negative x in my numerator. I'm going to make that a 1 in the numerator, and I'm going to bring the b to the negative x down as b to the positive x. Very important rules right there, and they must be automatic. Now, let's simplify. All right, so you're going to get problems where there's a lot going on with exponents and you need to simplify. And an expression is simplified when it contains neither negative exponents nor powers of powers. And this has both, so we got to clean it up. Okay, so first off, whenever I see negative exponents, I am going, and I have a fraction like this, I'm going to get rid of my negative exponent immediately. So the to the negative 2 became to the positive 2. And then I just need the reciprocal of this fraction right here. So b squared over a becomes a over b squared. So there's an easy way to get rid of negative exponents. Just make that base right there, do the reciprocal every time. Now here, negative 3, but I want it to be a positive 3, so I just need to replace a squared over b with b over a squared. Now, I don't have any negative exponents, but I still have power of a power here. So, next step. Well, a to the second power, a squared, and now I have b to the second, that's b to the fourth. B will be to the third power, and a squared to the third power would be a to the sixth. And now let's clean this up with some canceling right here. So let me see, what do I have for a's? Okay, oh man, my divisor are higher exponents for both of them, so that's going to leave me a 1 up top. And a squared over a to the sixth would give me an a to the fourth in my divisor. And b to the third over b to the fourth would give me a factor of b in my divisor. So there we go, simplified. We've got to get good at this. And again, do you agree this looks much simpler than our original expression? Okay, now, I've got negative exponents all over the place. And when you saw this the last time, we just got rid of the negative exponent out here by doing the reciprocal of the fraction. But I don't have a fraction here, so what am I going to do? Well, let's start rewriting this. So do you guys all agree that a to the negative 2 I could rewrite as 1 over a squared? And b to the negative 2 I could rewrite as 1 over b squared? Now, if I'm going to get rid of this negative exponent here, I need to write this as one fraction. So I'm going to go common denominator, a squared b squared. And what am I going to have to multiply this 1 by to get it over a squared b squared? It's only over a squared right now. I better make that a b squared. So make sure you see that. Does b squared over a squared b squared equal 1 over a squared? Yeah, because your b squareds would cancel. And here I better multiply this 1 by a squared, because a squared over a squared b squared would be 1 over b squared. Now, I know there's 2 terms in the numerator here, but this is one fraction. So now I can get rid of this negative exponent by changing this fraction to the reciprocal of said fraction. So my a squared over b squared will be my numerator, and my b squared plus a squared, which I'm a little OCD, so I'm going to write that as a squared plus b squared. And that is all to the first power, which I'm not going to write. Very cool. And again, much cleaner. No negative exponents, no powers of powers here. Here you see both. Okay. Now, all right. Okay, oh, look at this. Negative exponents and power of a power. Now, again, my first factor is a to the negative 2. So I'm picturing a to the negative 2 to the negative 1, and then b to the negative 2 to the negative 1. Now, all I'm going to do is go, my first factor is going to be a to the negative 2 times negative 1, that's a squared. And my next factor is going to be b to the negative 2 to the negative 1, that's a b squared. And there you go, much prettier than your original. So if you can get rid of negative exponents and powers of powers, you're going to take complicated expressions like you see on the left and make them much simpler like we see over here on the right. So let's do some more here. Now, I'm starting with 2 terms in my numerator, so I'm going to start by writing this as 2 separate fractions. So let's see, I have an x to the 5th over x to the negative 3. And then I have an x to the negative 2 over x to the negative 3. All right. Now, let's simplify each fraction separately. So, I need to get rid of this negative exponent. Can't I bring this up as x to the third in my numerator? And then I'm picturing x to the 5 times x to the third, x to the 8. I'm going to bring this x to the negative 3 up as a factor of x to the third in my numerator, and then I'm picturing x to the negative 2 times x to the third. Add those exponents. That's going to be times x to the first, or x. Or that's a plus right there. I'm adding. And there's my final answer. All right, now here. Now the easiest way to do this, you've got to first get rid of this by bringing it up to the numerator as x to the third. So I'm going to go x to the fifth times x to the third. And then what do I have left? I still have that times x to the negative 2. Now I could have brought that down as x squared, but most people find it easier to look at just like this, because now I'm going to go x and I'm just going to add those exponents. X to the 5 plus 3 is 8 plus negative 2. That's x to the 6. So I would like you guys to do 5.1, 1 through 12, and then 13 through 43 odd. And these are all laws of exponents problems. You're going to have to simplify expressions, and you have got to be really, really good at this stuff. So do these problems carefully. And if you go all the way back to this slide right here, and you know this, apply it, and this stuff becomes just automatic. Now this is a review of advanced algebra, and I'm expecting you guys to be really, really good at all this stuff. So one more time, let's go back to our homework. And here it is right here, 5.1, 1 through 12, and then 13 through 43 odd. And get a hold of me if you're struggling with anything. Thank you.